Thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. My name is Arya Mandaliza, a PhD student of Politecnico di Milano of Mechanical Engineering. And this is the title of my presentation, which is Numerical Modeling of Middle Instrument Rock Material under Fracture Test for Finite Element, coupled to SVH. So, as a motivation, you are working on the rock drilling project, so we estimate the variability of the rock. So basically, we are working to find a numerical model that can be used as an alternative to the experimental test. Therefore, we have performed some studies and unconfined compression tests and the resilient tests in order to define the unconfined compressive strength and the principal tensile strength of the middle strength rock material called Selena. In these studies and in today's presentation, I will present something about the Flexural test, which can be used in order to validate the numerical result that previously calibrated and prepared. So, as the outline, I will show something about the experimental tests that were conducted in the Class C laboratory of Politecnico di Milano based on the protocol of ASTM standard and the numerical models which are replicated in LSTime commercial software in conjunction with an advanced material model which is called KCC or MAT72R3, and finally the numerical resultant to experimental one will be compared to each other. So this is the configuration of Flexural test which is suggested by ASTM standard. As can be seen, there are two compressive rollers and two fixed one. Due to the symmetry of the configuration, it is anticipated to have almost constant shear stress in the compressive zone, and also accordingly zero bending moment in this area. Therefore, it is anticipated to have tensile and compressive stresses below and above the neutral cross-section respectively. So, we perform the Flexural test based on the ASTM standard with this designation number. So, of course, two pairs of steel rods, displacement control loading. The velocity is 0.2 millimeter per minute, and the Flexural strength can be defined by means of this equation, where the W is the maximum measured load, L, E, and D are the length, weight, and the thickness of the specimen respectively. With these values, however, the total length span of the specimen is 381 millimeters. So, in terms of numerical modeling, it has been already many numerical methods developed for rock mechanic problems, which are like finite element methods, SPH, discrete element, and many other methods. What we've used is the FEM coupled to SPH, and in order to have an idea about this method, let's simply define the pros and cons of finite element method, which is highly accurate. In finite element method, we have highly accuracy and convenient computing cost. However, the FEM usually is unable to deal with highly distorted elements. On the other hand, the SPH method is able to deal with highly distorted elements, but in comparison to FEM, it has less accuracy and more expensive in terms of computing costs. Therefore, there is another method called FEM coupled to SPH. It works like that: the mesh element remains there before reaching the highly distortion, and after that, the highly distorted FEM elements will be converted with the identical mechanical properties to either 1, 8, or 27 SPH particles based on what user defined. Therefore, this FEM coupled to SPH method takes advantage of both pros of the FEM and SPH methods. In LSTime, it will be performed in two different steps. First, by calling this keyword, which is called MAT erosion, which is an external eroding algorithm, which a user can define different criteria to eroding the elements. And after that, by means of this keyword that will solve it to SPH, the distorted elements will be converted to the SPH particles. As a material model, we use the KCC material model with Cartesian and case concrete model. In LSTime, the keyword which is defined this material model is called MAT concrete damage rate 3 or MAT 072R3. It is this material model was developed by Mulder from 19 The failure surfaces the failure surfaces consist of the multiplication of failure surfaces in compressive meridional multiplied by a function that represents the lower angle. Also, this material model consists of three failure surfaces, which are called yield failure surfaces, maximum failure surfaces, and virtual failure surfaces, which are defined by means of these equations. And another function which defines the radius of the biatoric plane. This function considers the couplet angle, which is proposed by Bill and Barkley. And however, this psi function is developed by Malver, which defines this function in different range of torsion. Then the relative position of current failure surface can be defined by means of two different linear interpolation functions that we have here. This eta parameter, which is called the damage parameter of KCC, and it itself is a function of another parameter in relation with another parameter, which is called lambda. This is accumulated effective plastic strain of KCC model. And itself, this lambda can be related to the effective elasticity. Then the KCC model also decouples the failure surface data from the volumetric deformation data. So, and equation of the state can be used in order to provide a function of current and produce volumetric descent for the current element pressure. In Elstein, the EOS that can be used is called EOS tabulated compaction that consists of 10 degrees of volumetric pressure and loading by moves. So it's possible to say that as an advantage of this model, it's very precise, but as a disadvantage, it's very complex, or at least very difficult to implement. Because it consists of 22 input parameters, 20 pressure volumetric equation related to the equation of the state, and 26 tabular data for defining damage model. Therefore, in the third release of this method, Malver developed an automatic input generation mode that predicted all these input parameters based on the uncombined compressive estimates. In order to show how this mode works, and also a modification, a very good modification of this prediction is presented in this article. So, in automatic input generation mode, the user can put the UCS and then put the UC uncombined compressive estimates in the KCC model and run the simulation and get the first set of results. However, at the same time, the KCC predicts all the other input parameters. So, it's possible for a user to use those input parameters and calibrate some of them, and again put in the KCC and run the simulation to get the more precise results. So, what we've done in our previous studies and also in this study is this for the matter of parameter identification. We used first the automatic mode of the KCC run. Unfortunately, we couldn't find any input parameter for the Pietro Serena Sanderson. Therefore, we used the parameters of another Sanderson, the Sanderson, which is supposed to be very similar to the Pietro Serena. Therefore, we put these parameters in the KCC, and beside the results that we got, the KCC gave us these input parameters. So first, we just calibrate the FD, which is the maximum principal, maximum tensile strength, according to the study that we performed on the Brazilian test, and also we calibrated these AI parameters. The AI parameters, as mentioned before, are used in order to define the failure surface in compressive meridian. So they can be calibrated by means of the experimental data of triaxial compression test. So we found this data from this article, and by means of careful fitting, we calibrated these AI parameters. These are the other specifications of the model, so the number of elements, nodes, symmetric planes, number of parts, the bonding conditions, contact treatments, and also the conversion criteria. So this is a comparison of numerical results and the experimental one, as can be seen. The KCC automatic mode is just a rough estimation. However, it works by just one parameter, so not very bad. But in the full input mode, the simulation reaches better results, and it can be also better seen here when we compare the Flexural strength as an average value with the automatic one and the manual calculation. And problem here that the string level doesn't reach the experimental one. This is mainly related to the deflectometer that actually in ASTM standard there isn't any suggestion and guidelines about how we can capture the displacement data. Therefore, we just ourselves put a deflectometer, but this deflectometer was fixed to the fixture of the apparatus, which means that it captures all the displacement data below the specimen and between the specimen and the initial apparatus. However, in the numerical model, we try to consider also those components, but this is the best results that we reached out. And this figure represents the distribution of numerical stresses in x direction along length. And this one captured one times the before failure, and this is after failure. As you can see, the tensile and compressive stresses are appear below and above the neutral cross section. And also this figure represents actually the presence of the SPH particles can be seen here, which means this figure represents the failure pattern, and can be compared also to the experimental results that we have the failure just below the compressive rollers due to the contact forces. So, as the conclusion, we've discussed the experimental configuration of the Flexural test, which performed in the classic laboratory of Milano and based on the ASTM standard. Then the numerical simulations that are replicated this experimental test